Hey kids, welcome to section 6.3, the central limit theorem. Today we're going to learn how to use the central limit theorem to solve problems involving sample means for large samples. So in addition to knowing how individual data values vary about the mean for a population, statisticians are interested in knowing how the means of samples of the same size taken from the same population vary about the population mean. So for instance, suppose a researcher selects a sample of 30 adult males and finds the mean of the measure of the triglyceride levels for the sample subjects to be 187 milligrams per deciliter. Then suppose a second sample is selected and the mean of that sample is found to be 192 milligrams per deciliter. Continue the process for 100 samples. What happens then is that the mean becomes a random variable, and the sample means of 187, 192, 186, blah, 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 maybe up to 196, constitute a sampling distribution of sample means. So this sampling distribution of sample means is a distribution that uses means computed from all the possible random samples of a specific size taken from a population. So if you have the entire population of adult males and you take a sample of 30 and you find the mean triglyceride level, you could get 187. You pick another sample of 30 and find the mean triglyceride level, you could get 192. So if you try all these different samples of 30 and do it 100 times, you've now got a sampling distribution of sample means. And so if these samples are randomly selected with replacement, then the sample means for the most part will be somewhat different from the population mean mu. These differences are caused by sampling error. And sampling error is the difference between what the sample measure is and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. So you're never going to quite get exactly what the population mean mu is every time you take the different samples. So when all the possible samples of a specific size are selected with replacement from a population, the distribution of the sample means for a variable has two important properties. One, the mean of the sample means will be the same as the population mean. And two, the standard deviation of the sample means will be smaller than the standard deviation of the population. And it will equal the population standard deviation divided by the square root of the sample size. So basically, in summary, if all possible samples of size n are taken with replacement from the same population, the mean of the sample means, denoted by mu sub x bar, equals the population mean mu, and the standard deviation of the sample means, denoted by sigma sub x bar, equals sigma divided by square root of n. The standard deviation of the sample means is called the standard error of the mean. And so we have this new formula for the standard deviation of the sample means, and that's equal to the standard deviation divided by the square root of n. So basically, when you take these samples of size n from a population, the mean of the sample means is going to be equal to the population mean, but the standard deviation of the sample means is going to be equal to sigma divided by square root n, not just sigma. A third property of the sampling distribution of sample means pertains to the shape of the distribution and is explained by something called the central limit theorem. The central limit theorem says, as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with a mean mu and the standard deviation sigma will approach a normal distribution. As previously stated, this distribution will have a mean mu and a standard deviation of sigma divided by root n. So as I keep taking samples from the population and I increase the sample size, so I take a sample of 30, then I take a sample of 40, then I take a sample of 50, eventually the shape of the distribution of the sample means is going to be approximately normal. So if the sample size is sufficiently large, then the central limit theorem can be used to answer questions about the sample means in the same manner that a normal distribution can be used to answer questions about individual values. The only difference is that a new formula must be used for the z values. And so here's our new formula. The z-score is found by taking x bar minus mu and dividing by sigma over square root n. So two important things to remember when you use the central limit theorem. First, when the original variable is normally distributed, the distribution of the sample means will be normally distributed for any size n. So if the population is normally distributed, then the distribution of the sample means will be normally distributed. Second thing, when the distribution of the original variable is not normal, then a sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, the better the approximation will be. So if the original distribution is not normally distributed, then we have to have a sample size of 30 or more in order to use a normal approximation. So here's an example. AC Nelson reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. So a couple things to look at here. First of all, the sample size is 20. But that's okay because the original distribution is normally distributed, so I don't have to worry about sample size. Over here on the side, I'm going to write down that my x bar or my mean is 25 and that my sample standard deviation is 3. I also want to write that my n or my sample size is 20 children. So I want to see if the mean number of hours these 20 kids watch television is greater than 26.3. So we're going to draw a picture. We're going to put the mean in the center, which is 25. We're going to find where 26.3 is. That's on the right. And we're shading greater than. So when I find my z-score, I'm going to do 26.3 minus 25. And then I'm going to divide by not just the standard deviation 3, but 3 divided by the square root of n, which is 20. So it's very, very similar to the process for a normal distribution. But now that I have more than one child that I'm looking at, I have to take that into account when I calculate the z-score. So my z-score here is going to be z equals 1.94. That makes sense. I'm on the right side of the mean, so my z-score should be positive. Then to find the probability, since I'm shading to the right, I have to do 1 minus my value from my table. I look up the value of 1.94 on my z-score table and I get 0.9738. When I subtract that, I get 0.0262. So basically what this means is if I choose 20 children and find the mean of the average amount of hours that they watch television, that I have about a 3% chance that their average is greater than 26.3. So it's a pretty small window. All right, let's look at a second one. The average age of a vehicle registered in the United States is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that their mean age is between 90 and 100 months. So in this distribution, we have a mean of 8 years or 96 months. I'm going to put 96 as my mean because my standard deviation is in months as well, 16 months. I have a sample size of 36 vehicles. So I want to know if I take these 36 vehicles and find the mean of their average ages, that mean is going to be between 90 and 100. So I'm looking for these 36 cars together, not individually. So 90 would be on the left, 100 would be on the right, and we shade. So this is 90 and here's 100. I need to find two z-scores. And remember, when you do the z-scores, you need to include the square root of square root of 36 in the denominator. So we'll do 90 minus 96 divided by 16 over the square root of 36. This will give me a z-score of negative 2.25. Then I find my other z-score, 100 minus 96 divided by the standard deviation 16 over the square root of n 36. This gives me a z-score of 1.50, which is good. I'm on the right and the left side of the mean, so I should have a z-score positive and a z-score negative. To find the probability, I'm going to take the bigger z-score, 1.50, look it up on the table, and I get 0.9332. I'm going to look up negative 2.25 on the table, and I'm going to get 0.0122. If I subtract them, I get 0.9210. So this says that if I have a sample of 36 vehicles and I find the mean of their average ages, I will have a 92% chance that it's between 90 and 100. All right, let's take a look at one more. This is an interesting problem. It has a part A and a part B, and they're different. So the average time spent by construction workers who work on weekends is 7.93 hours, which is spread over 2 days. Assume the distribution is approximately normal and has a standard deviation of 0.8 hours. Find the probability that an individual who works at that trade works fewer than 8 hours on the weekend. So since it's one person, I'm going to just use the regular z-score formula. My x bar is 7.93. My standard deviation is 0.8. My n is 1. So when I draw my picture, I put 7.93 in the center. Fewer than 8 hours is going to be 8 shaded to the left. Now this is one single person. So my z-score is 8 minus 7.93 divided by the standard deviation of 0.8. There's no square root of the sample size because that would be square root of 1, which is just 1. This gives me a z-score of 0.09. If I look up this z-score on my z-score table, I get 0.5359. So if I randomly select one individual and ask them how many hours they worked overtime, I will have a 54% chance that it's less than 8 hours. So that's for a single person. Now, let's say a sample of 40 construction workers is randomly selected. Find the probability that the mean of the sample will be less than 8 hours. So now we're going to be doing the same values as up top. 7.93 is our mean. S equals 0.8 is our standard deviation. And this time our N is 40. So our picture is still going to be the exact same thing. We're going to put the mean in the middle, 7.93. We still have less than 8 hours, so we're still shading to the left. Where the difference comes in is when I calculate my z-score. I'm going to take 8 minus 7.93, but this time my standard deviation, 0.8, has to be divided by the square root of 40 because that's our sample size. This is going to give us a z-score now of 0.55. Notice that that z-score is greater than the z-score from part A. When I look up 0.55 on my z-score table, I get 0.7088. So now notice that when I find the mean of 40 construction workers, I have a 71% chance that their mean is less than 8. So as my sample size went from 1 to 40, the probability that I will be less than 8 hours is going to be increased. So the more the sample size increases, the higher the probability of those sample means will also increase. All right, so this page right here just has a summary of the different formulas, when to use square root n and when not to use square root n when you're deciding how to find the z-score. Okay, so let's look at an application. 20 students from a statistics class each collected a random sample of times on how long it took students to get to class from their homes. All the sample sizes were 30. The resulting means are listed. So 20 students in a class went and asked 30 different people how long it took them to get to class from home. And student one asked their 30 people, and they got a mean of 22 minutes and a standard deviation of 3.7. Student two asked a different sample size of 30 and got a mean of 31 and a standard deviation of 4.6. So each of these people, each of these students asked 30 people how long it took them to get to school, wrote down the mean, and wrote down the standard deviation. So question number one says the students noticed that everyone had different answers. If you randomly sample over and over from any population with the same sample size, will the results ever be the same? Well, notice that every time we got a different mean and a different standard deviation. And this is going to continue. Every time you take a sample size from the population, you will always get different numbers. So it is very unlikely that you would ever get the same results. That's because each of those sample sizes is different. And each of the people in the sample size is different. And so it's going to be a very small possibility that you would ever get the same results. It is possible, but it's very unlikely. Number two, the students wondered whose results were right. How can they find out what the population mean and standard deviations are? Well, an estimate for the population mean is to find the average of the sample means, and a good estimate for the standard deviation is to use the sample standard deviations. So, a good estimate for the population mean is to use the average of the sample means. Because you're never going to actually be able to find what the population mean is. The population is going to always be larger than anything you can calculate. So instead of going to every member of the population, you can just take a bunch of different samples, average those together, and that's going to give you your best estimate. And then a good estimate for the population standard deviation is to use the average of the sample standard deviations. It's the closest you're going to get. Okay, so input the means into a calculator and check if the distribution is normal. So if you take all the means, these 20 values, put them into your calculator, and you want to check to see if it's normal or not, well, you can make a histogram. So make a histogram. So I put the values into my calculator. And I got 1, 2, 3, 4, 5, 6 bars. So 1, 2, 3, 4, 5, 6. These are the means. And then I'm going to go up to 5. 1, 2, 3, 4, 5. This is the frequency. So down across the bottom, I got 14, 18.6, 23.2, 27.8. Basically, I just typed all this stuff into my calculator and said, make a histogram. And it gave me this picture. I went to 3, and then I went to 5 for a couple. And then I went to 1 for a couple. So there is my histogram. Well, looking at this histogram, it doesn't look extremely normal. It doesn't look severely skewed. I mean, you've kind of got this part going up and then kind of going down, but I'm going to say it appears somewhat skewed because it looks like there's a tail that's starting to form. Appears to be somewhat skewed. It's not significantly skewed, but it's definitely not normal. Okay, number 4, check the mean and standard deviation of the means. How do these values compare to the student's individual scores? So if you take a look at the mean of the sample distribution and you look at the standard deviation of the means, the mean was 25.35 and the standard deviation was 5.8. I used one var stats in my calculator to figure out what those numbers were. And so if you take a look and compare them to individual scores, a mean of 25, well, that seems maybe to be consistent. But take a look at the standard deviation being 5.8. Look at that. The standard deviation of 5.8 is greater than any standard deviation that we got. So that leads me to believe that this 5.8 is way larger than we got. And the 25.35 is fairly consistent with the values that we got when we collected the information. All right, one more slide. Number 5, is the distribution of the sampling of the means a sampling distribution? And we're going to say no. The reason why it is not a sampling distribution is because we only included 20 of the possible samples, and there are many more. So we're going to say no. It only included 20 samples of 30 people and not all samples of size 30. Check the sampling error for students 3, 7, and 14. So for student 3, the sampling error is found by taking the value and subtracting the mean. And so if we go back and look at student 3 had a mean of 18, and we had a sampling mean of 25.35. So to find the sampling error, we're going to take 18 and subtract 25.35. This tells me that my sampling error is negative 7.4. So that means that student 3's average from their 30 students was below the sample mean for for all the samples. If we look at student number 7, student number 7 had a sampling mean of 26. So I can do 26 minus 25.35. That's going to give me a sampling error of 0.6. So that one's fairly close. If I look at student 14, they had a sampling mean of 29 minus 25.35. That's going to give me a sampling error of 3.6. So then question number 7 finally says, compare the standard deviation of the sample of the 20 means. Is that equal to the standard deviation from student 3 divided by the square of the sample size? It should be the square root of the sample size. How about for students 7 and 14? Okay, so the standard deviation of the sample was equal to 5.8. And so they want us to check for student 3. Is the standard deviation of student 3 equal to the standard deviation divided by the square root of n? So if we look back at student 3's standard deviation, student 3's standard deviation was 2.4. If I do 2.4 divided by the square root of 30, am I going to get 5.8? Well, 2.4 divided by the square root of 30 is 0.4. So no. If we do it for student 7, student 7 had a standard deviation of 1.9. If I divide it by the square root of 30, 1.9 divided by the square root of 30, you got 0.3. Again, not the same. If we look at student 14, the standard deviation of student 14 was 2.4. If I divide that by the square root of 30, I again get 0.4, so no. So the answer is no, it is not that it is way larger. Okay, so that's section 6.3. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.